to our program. So before 1960s and all, we have only digital ICs like TTL and CMOS with fixed functionality. No other user have no option to change or modify their functionality. That is, they work according to the design given by the manufacturer. User expected from these ICs, designers started thinking of a methodology by which the functionality of an IC can be modified or changed. So this modification idea basically give the momentum to create a programmable ICs in the industry. So this is a classification of logic circuit with respect to standard, with respect to the programmable capacity. The first classification is standard logic circuit. Here you can see the function realize single function or set of function once defined with no possibility of changing. So it is a one-time programmable device. The manufacturer only can design the functionality of the device. When it comes to the programmable logic, the hardware can configure any time by the user program. That is the benefit of programmable logic. So there is a technology logic right? So we are using in using classic product or ICs to different categories. SSI stands for scale integrated system. Like that as a ultra large scale integration. So device we can start here from this to the most common and fixed function integrated. As I already said, fixed function integrated circuit, the manufacturer is programming the device. User cannot configure the device according to their need. This is a chip package, this is a chip, and these are the peripherals. Now, we are going to the topic programmable logic device or PLD. In many applications, PLD has replaced the hardwired fixed function logic device. So we will look into the applications and all in the next slide. So these are the different types of PLDs. SPLD, CPLD, Fpga. SPLD, simple programmable logic devices. CPLD, complex programmable logic devices. And Fpga, field programmable catering. These are the major types of programmable logic devices. And we can program the device with two methods basically. One is schematic entry, another is text-based entry. So now we are going to look into the internal architecture of all these logic devices. So before analyzing the architecture, we need to understand the symbology we are using for the architecture. Okay, so these are the two symbols we are using to represent the programmability of an hardware. If we use this symbol, this one specifies that this is a fixed connection. It is not reconfigurable or reprogrammable. And this is a second symbol. This symbol represents that this is a programmable or reconfigurable connection. And these are some circuits or some gates with symbolic representation. Here we are using the fuse structure. That means it is connected and the input is given to the gate inputs of the gate. Also, depends on the gate's property, we classified the programmable logic devices into three categories. One is PROM, programmable read-only memory. Second one is programmable array logic. Third one is programmable logic array. So this is the most important part. The first block we can see in PROM, the AND array is fixed. So that means we are not using this kind of fuses. It is not programmable. We will use fixed connections. But in the case of OR array, that is programmable. That means we can use fuses or a pass transistor to make it is reconfigured. The second category is programmable array logic. This is just opposite to the PROM or PROM. The AND array is programmable and the OR array is fixed. So this is the second classification, PAL, programmable array logic. The third one is programmable logic array. In this case, the both arrays like AND array and OR array, both arrays are programmable. So these are the three classifications of programmable logic device. And this is a structure of PROM. In this structure, we are giving two inputs A and B with non-inverted and inverted input, and the AND arrays are, like we said in the block diagram, AND arrays are fixed. That is a fixed connection. So for this gate, we are getting a min time of A bar, B bar. For the second connection, we are getting A bar, B. Third connection, A, B bar. Fourth connection, A, B. So these are the min times we are creating using this fixed AND array. And once the manufacturer is connected like this, it is not reprogrammable or reconfigurable. Now all these min times are available here, and we have a programmable OR array with fuses. In this connection, we can reprogram or reconfigure the device. For example, the function F1. We can create a Boolean expression in this OR function OR array, in OR gate, or this OR gate, or this OR gate, any OR gate. For the first OR gate, what we done is we connected here, 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 here. So all functions we are getting at the OR gate, first OR gate. And if you want to remove this min time, we can burn this fuse. So we will get only these three min times in this OR. So depends on our need or application, we can use these fuses. Another symbolic representation is, instead of using 4 lines, we can also use a single line, and we can connect like this. So this is a representation of PROM, programmable read-only memory, with fixed AND array and programmable OR array. So this is the next category. Here, the AND array is programmable, OR array is fixed. So you can just go through this circuit here. This is a circuit of programmable array logic. We are using fuses to connect various inputs to the AND gates. From there, we are fixedly connected to the OR gate. From there, we will get the output functions or Boolean expressions. So let us analyze the first expression. The first output is W, and the W is the output of first OR gate. First OR gate, we are connecting the output of the first 3 AND gate. Let's look at to the first AND gate. In this first AND gate, we are connected A, B, and C bar. So this min time will be, output of the first AND gate min time will be A, B, C bar. And next AND gate, here you will get A bar, B bar, C, D bar. So this will be the second minterm. Third AND gate, we are not connected any input, so we will not get any kind of output from AND gate to OR gate. So we are now getting minterms from the first two AND gates. So this is the function A, B, C bar plus A bar, B bar, C, D bar. So this is a method of programming in programmable array logic. Like that, you can also find out the outputs in X, Y, and Z. Very simple. We'll just look at the second output X. So what will happen here? We are getting input to OR gate from two AND gate. The first AND gate minterm is A. Second AND gate minterm is B, C, D. So A plus BCD will be the output of the next gate. So like that, depends on our need or requirement, we can reconfigure the device. So we already covered programmable array logic, programmable logic array, and programmable read-only memory. So first one is fixed AND array, then programmable OR array, that is PROM. Second one is programmable AND array, fixed OR array, that is PAL. Third one is programmable AND array and programmable OR array. Both arrays are programmable. So this is PLA. So this is PLA circuit. I just the slide, I think. So in this circuit, as we can see here, the AND array and OR array both are programmable. So fuses are there, and this is one symbolic representation, and this is another symbolic representation. And this is the initial one was the first hardware. We are not programmed anything. All fuses are in proper connection. Here we burn some fuses to get some Boolean expression. So let us look the first output from first OR gate Y2. In this OR gate, what will be the expression, Boolean expression? Last three AND gates are connected to the OR gate. So that means here we are connected A bar. This will be the minterm at first AND gate. This will be the minterms at second AND gate, and this will be the minterms at third AND gate. So A bar, B, A, B bar. So output will be A bar plus B plus A, B bar. This will be the output for Boolean expression we will get at Y2. So we can program both AND array and OR array. So this is an example for programmable logic array. So now we covered all three programmable logic devices. Now we will go to the industrial devices that is using this kind of arrays. First category is SPLD. This is the least complex form of programmable logic device. So programmable logic devices are using PAL, PLA, or PROM, and depends on the complexity. We again classified the programmable logic devices into SPLD, CPLD, and FPG. First classification is SPLD. In this SPLD, SPLD comes under SSI or MSI. That means small scale integration or medium scale integration classification. Usually, industry is having 24 to 28 pin SPLDs are available. With the categories are PAL, GAL, PLA, PROM. We are using all these kind of architecture or arrangement for SPLD, creating SPLD. Another classification is CPLD, complex programmable logic devices. This one is having much higher capacity than SPLD. So that means more number of logical gates and programmability fuses. That means we can create more complex function in this CPLD compared to SPLD. The CPLD is equivalent to 2 to 64 SPLDs. So that is the capacity of CPLD. It is much complex than the CPLD device. And in industry, you will get 44 pins to 160 pin packages, depending upon the complexity of the CPLD devices. So there are several forms of CPLD which vary complexity and programming capability. And we will look at the architecture of the CPLD. So the basic architecture of CPLD contains a functional block, interconnect matrix, and IO block. These are the three blocks of CPLD architecture. The functional block contains the programmable logical circuits like PAL or PLA, and interconnect matrix basically helps to connect between the blocks and also between the blocks and IO input output blocks. And this input output blocks, through this port, the external environment can communicate to the CPLD device. So this is the basic architecture of CPLD. Functional block will be there. Inside functional block, we can create different types of logical devices, or we can create different types of Boolean functions. And using this interconnect, we can connect between functional block and also functional block to the external world. This is another architecture figure. Here also you can see different IO blocks, the connecting channel or the connection matrix, and logic blocks. So this is an example for CPLD. As I said, there are different packages available in industry for CPLD. These are the examples. One is 84-pin PLCC package. Another is 128-pin PQFP package. So just compare these CPLDs with our TTL ICs like 7400, 7402. We have only 14 pins to 16 pins, and that also in DIP package. Compared to those kind of devices, this one is much complex. Even the pin itself shows that how much complex is the system. We have 128 pin and 84 pin. Now we have the next category. It is Fpga. It is field programmable gator. It is slightly different from SPLD and CPLD, and greatest capacity compared to any other logical devices. The greatest capacity itself shows that it is having more number of logic blocks and transistors. Consists of an array of anywhere from 64 to thousands of logic gates or groups that are sometimes called logic blocks. So like since CPLDs also have logic blocks, but compared to CPLD, FPGA is having 64 to 1000 logic blocks are available. You see two classifications of FPGA, coarse-grained and fine-grained classifications. And FPGA pins, the industry FPGA comes from up to 1000 pins or more. Means CPLD we have only 128 pins or 84 pin package, but for FPGA you have thousands or more pin package available. That much complex system. And this is the architecture of an FPGA. Like a CPLD, it is also have three blocks: CLB, switch matrix, IOB. CLB stands for configurable logic block. Then switch matrix basically programmable interconnects. And third category is IO block. So these are the three building blocks in field programmable gate array. So we'll look into each part. Another architecture figure. These are the CLBs. These are the connection lines. Okay. Now this is a logical element or a CLB, configurable logic block. This is a simple one. It depends on the FPGA family. The complexity of the logical blocks will change. This is the most simplest form to understand the basics. I'm just explaining the basic CLB element. In this CLB, we have a lookup table, and also we have flip-flops, and also multiplexer, then buffer. These are the basic structure of a CLB. The purpose of lookup table to create Boolean expressions. So it depends on the requirement or depends on our need, we can create different types of Boolean expression using lookup table. And also we can make the circuit to a sequential one using a clock. Most of all the FPGA is manufacturing with a global clock. So using a global clock, we can create a sequential circuit with a FPGA. So this is a CLB, configurable logic block or logical element. This is a structure. So we are using multiplexer, flip-flop, and lookup table. These are the various functions implemented inside the lookup table. Here, this one is for 3 to 8 decoder. So we are using 3 input, then 8 output. So this functionality of truth table we can create using our lookup table, and we will get the output here. If you need to make it sequential, we can use this block. This is one example of FPGA family XC3000 CLB. In this structure, more number of transistors and CLBs, and the complexity of CLB is slightly higher compared to the first one. Here we have more number of multiplexer, flip-flops, and then lookup table is having more number of inputs. So this is an example of CLB. Another block is programmable interconnect. So we already covered the first 2 blocks. The first block was these are the 3 blocks. Configurable logic block. So what is configurable logic block? We can create Boolean expressions with the help of programming, and with that, according to that program, the lookup table will create the Boolean expression. So programmable logic. And next block is programmable interconnect. Programmable interconnection resource FPGA provides a routing path to connect input and output of the IO blocks and CLB. So IO blocks and CLB into logic network. So in the connection, to establish the connection between logic blocks and also to the input output or to the external world, we are using programmable interconnect. So using programmable interconnect, the CLB can communicate to IO blocks, or CLB can communicate between each other. So all these are made possible by the programmable interconnect. We can use pass transistor. Specially designed pass transistor is controlled by a configuration bit, form programmable interconnect points, and switching matrices used to implement the necessary connection between selected metal segment and block nodes. So when you are implementing a system, we are not 100% utilizing the CLB blocks. Maybe we are selecting 1, 2, or maybe 100 CLB blocks in the FPGA. So whichever the block we are selected for implementing a system, all these blocks are interconnected with the help of PIP or programmable interconnect point. The programmable interconnect point is a pass transistor controlled by a memory cell. The wire segment of each side of the transistor are connected depend on the value in the memory cell. The pass transistor introduces the resistance into the interconnected path and hence delay occurs. So one aspect is that when we are using this kind of pass transistor model of programmable interconnect, the interconnect is made programmable, but it will create a path delay. That means when you create a system, in that system, apart from the gate delay, it also produces a considerable path delay. So we need to consider when you are implementing a system, we need to consider both path delay and gate delay.
Okay, so we have few questions in the Q&A section.
Okay.
First question is, What is generic array logic and how does it differ from PA and PLA?
Okay, fine. Yes, it is basically almost similar to PROM, but the difference is that the ROM is electrically erasable. So that is the only difference between GAL and other logic. In PROM, it is not electrically erasable. That is a structural difference, and I will send you the details. If they send me mail, I will send the complete structural details. Any other doubts?
The next question is difference between FPGA and microcontroller.
Okay, fine. So FPGA, basically that's why I shown you the structure of the transformer board. In microcontroller, we are creating an architecture. Let us take an example of 8051, or let us take an example of Hvga 328. Hvga 328 is a microcontroller inside Arduino Uno. So after manufacturing the microcontroller, it is impossible to change the architecture inside that microcontroller. We can just give the program according to the architecture. If architecture is not having that capability, for example, let us take an example. Suppose the architecture inside Atmega 328 support 10-bit ADC, and you are going to design a system that need 12-bit ADC. So at that moment, when you are using Atmega 328 microcontroller, it's impossible to use that system. But if you use FPGA, we can create a 12-bit ADC. We can suppose the FPGA is having 10-bit ADC, we can reconfigure it to 12-bit ADC. So that means the hardware itself we can change in FPGA using a hardware description language. But in microcontroller, whatever the hardware available or existing, we can only make use of that. So that is the difference between FPGA and microcontroller. I hope you are clear about the difference.
Yes, sir. That's all. The 2 questions we have in the Q&A session. You can please continue.
Okay, fine. Thank you. Okay, so we are discussing about FPGA. There are many industries, they are manufacturing FPGA with different types of architecture. These are the different examples of FPGA vendors. Xilinx, Ultra, Atmel, Lattice. They are using SRAM based FPGA, and Flash and anti-use kind of FPGA, Actel and QuickLogic. These are the various FPGA vendors available in the world or in the market. And Xilinx and Ultra share 60% of the market. Usually, in any academy or any industry, if you go or if you observe, most of them are using FPGA manufactured by Xilinx or FPGA manufactured by Ultra. These are the different applications of FPGA. It is used in consumer electronics, security system, video image processing, defense, aerospace, wireless communication, medical electronics, everywhere we can use. Not only in this domain, nowadays everywhere we are using FPGA, and they are replacing the ASIC or non-programmable IC. So the applications are actually expanding every day, FPGA applications. The benefit is that suppose if you are using in consumer electronics, and if you want to upgrade the system, we don't need to change the hardware. You just need to go with a program, burn that program to FPGA, and according to that program, FPGA will reconfigure into a new structure. So that means the replacement of the material cost we can reduce using FPGA, and also upgradation is also possible. So these are the various VLSI industry, and there are a lot of career opportunities in this domain. EDA company, ASIC, FPGA, everywhere you go, you need to have a thorough or proper understanding of programmable logic devices. These are the leading companies: Xilinx, Ultra, Texas Instrument, Intel, Cisco, TSMC. TSMC basically create DSP modules. So for all these systems, we need to have an understanding of programmable logic system, and also we need to understand the hardware description language. So I will just demonstrate one programmability of FPGA, how to program an FPGA, and how to create a program, and how to create a structure using that program. So that is the next example. So as you can see, this is a truth table of half order, sum and carry. And with this truth table, using graphical method or tabular method, we created functions or Boolean expression. For sum, the Boolean expression is AX or B, and for carry, the Boolean expression is AB. And this is the block representation: two entities at the input and two entities at the output. So this is the block diagram, truth table, and circuit diagram or logical diagram. Now, this is our objective. Now, how to create the system in FPGA? So, that is the real challenge. For that, we are using hardware description language. Using this language, we can express any hardware, whether it is processor, whether it is DSP module, whether it is mathematical module, or whether it is any other logical module, any kind of module we can create or express with the help of HDL. And HDL basically introduced in 1970s. The first HDL language was VHSIC HDL, very high speed integrated circuit HDL. So this was the first language. And in 1980s, another language also introduced. That language is Verilog, and this is inspired by the C programming language. Also in 1980s, this VHDL language is standardized. And 1990s, Verilog also standardized. Okay, so now we are using in industry two language, VHDL and Verilog, for creating various hardware. So I will just show you the demonstration of the Verilog program and how, after burning or after doing the program, how it is the architecture or the hardware is reading these expressions and how they are creating the hardware. So that is the main objective of this course. We need to understand how the system is working. So here I am using a simulator, and the simulator is designed by Xilinx, one of the leading FPGA manufacturing company. The simulator name is ISC. So I will just create a new project. Is this tab is clear? This one icon, new project to start. Okay. So here you can see product category: general purpose, automotive, military, radiation. There are various applications. Any application we can use our FPGA module or programmable logic devices. I am just selecting general purpose. Here we can see various family. So all these are FPGA or FPGA family created or made by Xilinx. So all these devices we can simulate and program using Xilinx ISC simulator. This is an old simulator. Now the industry is using Vivado simulator. I don't have that software, so that's why I am showing in this ISC simulator. I am selecting a hardware called Spartan 3. This is a logic family or FPGA family from Xilinx. And here we can select the devices. Under Spartan 3 family, you have different types of devices, depends on the hardware complexity. You can select any hardware, depends on your project or your requirement. Another important factor you need to select is the language. So as I mentioned earlier, we have two hardware description language. One is Verilog, another is VHDL. You can select anything. Okay. So now I created a project for a specific programmable logic device. So my objective is to design a half order. So this is the case where we can express our hardware using hardware description language. We have two inputs. I'll use the symbols A and B, and two outputs. So once you define the directions of the variable, IO blocks will work according to that. So here we have two entities as input and two entities as output. So from the truth table and from the circuit diagram, it is clear that the expression for sum is A XOR B. For that, we are instantiating XOR, and XOR is already inbuilt available in this software. So we just need to instantiate that XOR for this expression. And also carry expression is A and B. So we just instantiated AND gate in this tool. So now our program is completed. This is called structural programming, structural model. We just explain the or express the structure, describe the structure of the hardware. So this was our objective. Okay. So now we made a block. So this is having two entity. This was our objective, two input entity and two output entity, sum and carry, and two inputs. So as I mentioned earlier, we have logical blocks. Inside logical block, we have lookup table. So two lookup tables were taken. Lookup table from second block, eighth logical block. Lookup table from the second block, sixth lookup table. Two lookup tables were taken for creating the Boolean expression. The first lookup table, let us see. So this one is for the carry. To create a carry, we need an AND gate, and this AND gate is created at the first lookup table. This was a truth table, and this was a KMR for the carry. And second lookup table, you can see truth table for the sum, graphical optimization for the sum, and this is a schematic. A bar, B, A, B bar, then OR gate. So we are getting an XOR expression A bar B plus AB bar. So whatever we explained in the theoretical portion, the same thing is actually we can observe here also. Lookup table, then buffer, then input. Since it is a combinational circuit, we are not connected any clock, or else we can see the clock circuit and flip flop and everything in this schematic. Now, will take some time. Okay. So this is the internal structure of the FPGA that I selected, and these are the logical blocks. And when a programmer is implementing a system, the programmer need to place which logic block, and programmer need to route the logic block to the output. So these are the logic blocks in the hardware. You can observe clearly. Yeah. Various slices available. These are the interconnects, programmable interconnects. Okay, so these are the hardware detail. This is the programmable interconnect. These are the slices, and we have I/O blocks. So all these are under single system. We can analyze it using this. Now, apart from this, the advantage of using FPGA is that we have inbuilt cores. So that means when you are implementing a system, let us take automotive system or communication system, DSP system, we have inbuilt system available in FPGAs. So we don't need to do extra programming. We just need to burn this program to the hardware. For filter, correlation, modulation, transforms, any applications, inbuilt cores are available in FPGAs. So the implementation complexity is also reducing. So that is the advantage. So these are the, if you go through this kind of IP core itself, you will understand that you have a lot of applications in PLD, automotive industry application, communication and networking application, digital signal processing application, various math function creation, then bus interfaces. For example, PCA Express, all these are parallel communication standards. So we can implement this kind of parallel communication bus interface using FPGA. Then storage area network, video processing. So even video processing, image processing also we can implement using FPGA. So that is why I explained in the PPT that we have different types of applications. So all these applications are possible using FPGA because we have that much hardware capacity and complexity in your system. You just need to express all this requirement in hardware description language. According to that language, FPGA will create the hardware. I think I completed the demonstration. Now we'll just go through the previous year questions that were asked from PLDs, programmable logic devices. This was the one question I have seen in last year exam, 2018 exam. What are FPG and PLDs? Very simple question. So they are not asking in-depth questions from this topic. Using suitable PLA, design a 4-bit binary to gray converter. So we already know how to implement a Boolean expression using PLA, PAL, and PROM. Write a short note on FPGA. That was also very simple question. Then PAL, PLA, and FPGA. This was a 20-mark question. And what is FPGA? What are its application? With block diagram, explain its internal structure. So we already explained the block diagram, 3 blocks, CLP, interconnects, and I/O blocks. And we already know what are the applications of FPGA and what is FPGA. So these are some reference. Okay, if you have any doubt, you can ask.
Yes, sir. Question.
Okay.
Can FPGA used as a replacement for CPU?
Pardon, I am not able to. This voice is not clear.
Can FPGA, sorry, sir, can FPGA be used as a replacement for CPU?
Yeah, definitely. Because before creating the processor, basically they are testing in FPGA only. And also, right now, Intel, they are creating a system with combination of processor and FPGA. And in future, I think they are already going to the FPGA kind of processor, because they can reprogram it, or you can update the architecture. Definitely, CPU can be replaced by FPGA, because FPGA has the capacity and complexity to create a CPU system inside that FPGA. Any other doubt?
Okay, sir. Another doubt is regarding the simulator used. Is the simulator used for the demonstration freely available for the students?
This is an older simulator. This is called ISC simulator. Vivado also available in the internet. You can download, but we can only implement less complex circuit using Vivado if you don't have the license. If you purchase the license, you can create bigger systems and more complex system. Otherwise, you can download Vivado. The name is Vivado. If you have doubt, just mail me. I will send you all the details about the open source and all this kind of simulator and tools we are using to design programmable logic devices.
So students are asking your mail ID. They are asking to display
Sure.
the mail IDs again.
Sure. So these are my communication. This is my official mail ID, and this is my IEEE mail ID. You can send your queries or any of this. And if you want to implement any system as a part of your course project, definitely you can use FPGA. You can implement, and also the testing is also very easy. If you have time, I can show you how the test benches work.
Okay, sir. Sir, those were the questions in the Q&A section. So you can.
I will show you how to check the functionality. Okay, so this is called test bench. So whatever we created or expressed using hardware description language, we can check its functionality. So here, whatever we defined as input entity will come as register, and the output entity will come as wire. Now we need to begin with the values. So here initially I have given 0, 0 at the input. After that I will give 0, 1. Then another 3 input combinations, 0, 0, 0, 1, 1, 1. Just to understand how it's working. Actually, I installed with ISC simulator, but the simulator right now it's showing model sim. So I need some time. So I will mail you the details and all about the simulation. Here we need to see ISC simulator. I will show you this. These are the properties that we selected. Here right now in this tool, I can see only model sim and PCS simulator. So once you have ISC simulator, you can easily check for the functionality of the device. To check the functionality, you need this test bench. So in this test bench, you can give input like this, which 00 stands for #10 stands for the delay, nanosecond, delay in nanosecond. So after input 00, it will wait for 10 nanoseconds and it will give input 01. So then it will work for second input. And after again 10 nanoseconds, it will work for 1. So once we verify the functionality using the simulator, we will burn all these programs to the hardware. For that, we need to connect the hardware. Then we need to configure the target. So this is the option for configuring the target. So right now I don't have the hardware, so I'm not connected the hardware. If you connect the hardware, it will show here. Then we just need to burn it. So once you burn the program to the hardware, depends on the lookup table we mentioned. We can place it there. Two lookup tables they will use for the hardware, and we will get the half order circuit in Fpga. And like one of you asked about CPU, we can create the processor, 4-bit processor, 8-bit processor, 16-bit processor, or 32-bit processor. Once you express the processor hardware or architecture in HDL language, we can burn that hardware to the Fpga. Then Fpga will act as a processor. Any other doubt?
There are no other doubts. Can we summarize the session?
Yeah, sure. So our topic was PLD. In syllabus, basically, they are not covering this much depth. It's simply asking about these two categories, PAL, PLA, and PROM. And all these are made with the help of programmable logic gates. And for program, we are using this kind of symbology. And we are using arrays of AND array and OR array. Depends on the programmability of arrays, we are differentiating all these devices. With the help of these arrays, we are created SPLD, CPLD, and FPGAs. And these are the various architecture. These are the ICs available in industry with different set of packages. For example, if you want to implement a 4-bit processor, you don't need to implement using FPGA. You can use CPLD. CPLD hardware is enough to design a 4-bit processor. But when it comes to 16-bit or 32-bit processor, you need a bigger system, bigger FPGA, and we need different types of family like that is shown here. Yeah, Xilinx or Ultra family, they have Vertex or higher versions of FPGA family with billions of transistors. So transistor count and logic blocks are the important factor. Using this factor, basically that will decide how much bigger system we can implement in FPGA. And these are the application. Everywhere we can use FPGA. We can replace microcontroller or any other system because this is reconfigurable. And once you need to update or upgrade the system, you just need to burn the HDL program. According to our program, you can create any kind of hardware. So finally, we'll just conclude that this is simply like a transformer board. So it can change to any structure, bigger structure, smaller structure, depends on our need. Thank you.
Thank you, sir, for your valuable session. Thank you, participants, for this session.
Okay, and
so there
is a request. Can we get this presentation? Definitely, I will share with Lakshmi, and she will share to you. Or also, you can mail me about your doubts. I will reply in that.
Okay, sir. Thank you.
Okay, thank you, sir.